So moving on to the electrolysis of aqueous solutions, there are a few certain rules that we need to follow. And I'm going to explain those rules first. Those rules are actually going to work as tips as well, since the rules or the explanation of this stuff is usually not asked as a part of exams. They simply try to ask you about the products or about the equations, which one is going to go to which specific electrode or observation. So this can be easy. Okay. So this would work as tips, even if you don't understand the whole concept and you understand two simple tips, you can every time get the answer to a question of electrolysis of solutions correctly. Okay, now before I start with rules of cations and all these headings, there is some prior knowledge that I'd like to update you with. Now, as soon as I use the word solution, we're talking about aqueous solutions. Let's take the simplest examples. Sodium chloride is the simplest of ionic compounds, the table salt that we eat every day. This is the most simple example and the very first example we start our ionic compounds with. Now, whenever I use the word solution, it means a little bit of sodium chloride is dissolved in water to form a solution. You may dissolve more, you may dissolve less. It entirely depends upon you. When I talk about this way, I hope you understand that sodium is going to form positive ions in the solution. Chloride is going to form negative ions in the solution. Aqueous represents water, the formula for which is H2O. Now, water is a covalently bonded species, but there is something very important about water. When we try to pass electricity through water, and water has some salts added to it, water tends to decompose not as a covalent compound, but just like ionic compound. It starts giving away some ions. And what are those ions? Let's clarify. Water is going to give us an H positive ion, and it is then going to give us an OH negative ion. So every time we have something made in a solution, these two ions are a must. You may change the salt, these two ions may change, but H and OH will always be there. Now, in the previous example, we had NaCl, which gave us Na positive ions and Cl negative ions in the example of molten, right? So there was only one positive ion and one negative ion in the previous examples. The positive ion used to go to cathode, the negative ion used to go to anode. But in this example we are about to begin, there are not one positive ion and a negative ion. The problem is that we have two positive ions, H positive and Na positive, and we have two negative ions, Cl negative and OH negative. Now, when we're going to turn on the battery and the current will start running through the solution, actually the positive and the negative ions will start competing with one another. What's the competition about? The competition is about going to get to the electrode and get deposited over there or be converted over there into some other species. That's what the competition is about. Although the simple concept explaining this says the more reactive stays inside the solution, the less reactive goes to the respective electrode. All right. But let's start with our tips. Let's start with the working. I am going to divide it as two-part portion. Part number one, rules for cation. How would we know out of Na positive and H positive, which one is going to stay inside the solution and which one is going to go to the electrode? Then moving on to the next page, I will discuss rules for anions. And again, in between these chloride ions and these hydroxyl ions, I'm going to explain to you which one will stay inside the solution and which one is going to go to the anode. All right. So let's start with rules for cations. You'll come to understand out of these two cations, Na positive and H positive, which one is going to stay inside the solution and which one is going to go to its respective electrode. Now, the rules for cations are pretty simple. We use the reactivity series. The reactivity series is present on page number 216 in figure 8.11 on fourth edition of the book. So what I'm going to do is that let's keep this writing over here. I'm going to get back to the book. This is chapter number 4. And we've just started electrolysis of solutions. And instead of studying anything from here, I'm going to take you all the way to chapter number 8. And this is page number 216. And this is figure 8.11 that I was talking about. Now take a look at this figure. You're going to find a huge long list. And on the right of your list, it tells us that this list is based upon reactivity, this portion, and it is actually telling us that the reactivity is increasing from bottom to top. I'm going to temporarily erase everything. Now, the elements on the top are the most reactive elements in the reactivity series. And then you can see something, then all the other elements' names are written in the similar way. However, we have two elements for whose the name are written in brackets, one over here and one over here. Consider them as junctions. Why? This list is entirely made up of metals, and these are the only two non-metals in this list. Okay? One of them is carbon, which is up top. The second one is hydrogen, for which I'm mentioning it's a part of non-metals over here. So then there is a central portion. These are the elements which we can safely call as moderately reactive. And then there are a few elements at the bottom in the blue part of the diagram. And we can safely say these are the least reactive elements. You're supposed to remember this reactivity series by name. This seems like a difficult task. We usually don't ask IGCSE students to go ahead and cram stuff like that. But they're easy mnemonics that works for it. And thanks to a few students of mine in past, I've actually been loving their ideas since they always come up with some funny mnemonics to remember it. Now, student in my class, instead of remembering these elements through their names in the appropriate order, and let me tell you, the order from top to bottom or bottom to top really matters. That actually may matter most. He instead remembered these, right? The symbols. And he remembered them in a pretty funny way. Look at it. K, Na, Ca, Mg, Al, C. He remembered it as Kanaka Magal C. And it sounds funny. It sounds something gibberish, but it's a really good way to remember it. And he remembered the whole thing. It was really funny when he used to say it out loud. Kanaka Mogal season Bub, something like that. I don't even remember the whole thing, but I do remember his start. He always used to start with it. And I actually recommend my students they can go with any funny mnemonic, anything easier to remember the entire reactivity series. This is going to help you a lot with electrolysis. I've seen students.
Sir,
Go ahead.
sir, what mnemonic did you use in your time when you were remembering the reactivity series? Which you found it, better, or that was suitable to you?
You're not gonna believe me. Okay, I completed my matriculation back in 1999, and you'll be amazed to know there was no reactivity series back then. So I never had to memorize it.
You're really lucky then.
Yeah, students keep calling me that. They tell me all the time, "Sir, you're lucky you never had to memorize this and that." But let me tell you, you memorized less number of things as compared to what we used to memorize. The study was not that easy, and all you had to do was memorize back then. I had to memorize my entire course, not just one thing. But even if I have to remember this way, see, that student was taking it as fun, but his Kanaka Magalsi is something that I remembered. Though I don't remember the whole of it, but I remember some of it. Good enough for me to remember it. But if you ask me how do I remember it, I actually break it into parts. I used to memorize first five, then these four, and then these four, part by part. That's what I usually do. That's what I do with most of my stuff. I break my stuff down into smaller compartments, smaller portions, and then I try to memorize them portion by portion. That's one of the best ways. One of the most difficult things to memorize in the world is one of the most used or read book in the world, which is Quran Majid. And people actually break it down into smaller parts and then they memorize it part by part. That's how we have been producing the memorizers of Quran Majid all around the world. So yeah, it's a pretty effective way. Break it down into smaller chunks. Try to memorize one chunk after another, try to connect the dots. And this is a perfect way to do it. All right. However, there is another funny mnemonic. Since we are at it, let's talk about it. Potassium starts with P, sodium starts with S, calcium starts with C, magnesium starts with M, aluminum starts with A, carbon starts with C. There is a famous sentence, please send camels, monkeys, and alligators. The list goes on with different names of animals. I don't remember those names. And then this it goes with in tight, large, heavy crates soon, something like this. And then there is names of animals in between: alligators, cats, zebras, in the large, heavy crate soon, something like this. So you can either remember this funny sentence about a zoo, or you can remember this Kanaka Magalsi, or you break it down into smaller chunks. Whatever you do, you need to memorize the entire reactivity series. Well, I'm not asking you to memorize all of it today, okay? So I'm gonna make it easier for you. Let's erase all of this. We are gonna not do any of these parts for today. So for today, it's just this part, okay? Hydrogen and elements below it in its appropriate order, which is pretty simple. Hydrogen has just four elements below it: copper, silver, gold, platinum, the most expensive metals around the world, at least one of the most expensive metals around the world, okay? So it's just hydrogen, copper, silver, gold, and platinum we're going to use in electrolysis. Again, I'm going to erase all of it. I'm going to go back to the original document we were studying from, electrolysis. So my tip is simple. If the salt name or salt formula contains elements such as copper, silver, gold, platinum, these are symbols for it, they are deposited at the cathode. If the salt is not made up of these elements, but is made up of any other element, be it sodium, calcium, potassium, magnesium, any other element from the reactivity series, or other than the reactivity series, hydrogen gas is produced at cathode. And hydrogen gas is always produced with this equation. So it's pretty simple. On the other hand, since we know the actual principle, more reactive ion stays inside the solution. Okay, he's making a lot of mistakes. Since a student compiled it, he has made a lot of mistakes. Okay, so more reactive ion stays inside the solution. The point I'm trying to make, since I started this off with NaCl aqueous, so I'm going to rewrite it. This gives us Na positive ion, Cl negative ion. This gives us H positive ion. Aqueous means water, and OH negative ion. Right now, since we are doing rules for cations, there are two in between the competition is arise, Na positive, NH positive. So more reactive stays inside the solution, which means Na positive, since is more reactive, stays inside the solution. Hydrogen is going to go at cathode, and hydrogen ions are going to produce hydrogen gas over there. Make sense? So the tip
Yes,
is
sir.
pretty easy. If you have these four elements as a part of the name of the salt or the formula, they will form at cathode. Otherwise, for all the elements, hydrogen is going to form with this specific reaction. So you need to memorize this reaction. Okay. Moving on. The genetic rule for ions is that more reactive stays inside the solution and less reactive is the one that gets to the respective electrode. Okay. Rules for anions. Now, in case for rules for anions, we actually bifurcate them in two categories. Number one is simple anions, and number two are polyatomic anions. So this is all of it is category one. All of this is category two. Now, simple anions are chloride, bromide, or iodide, and they are compared with OH negative, since again, Cl in aqueous system are going to form Na positive and Cl negative, H positive, OH negative. Now, if we talk about anions, there's the competition between these two anions. So everything is going to compete against OH negative, since every time, if there is a solution, OH negative ions will be coming out of water. Make sense?
Yes, sir.
Okay, then if that makes sense, this time we're competing chloride ions against OH negative ions. For these, the tip is it depends upon the concentration of solution. So if the solution is concentrated and the word concentrated will be mentioned as a part of the question, the halide ion will go to the anode and will form the halogens, the diatomic molecules. If the solution is not concentrated, the word dilute must be mentioned with it. Then OH negative ions, since they are so high in concentration, since dilute means very less amount of salt is used and a very good amount of water is there. So there are so many OH negative ions, since there are so many, they are get succeeded in going to anode and forming oxygen gas through this equation. This is the second equation that you are supposed to memorize. Okay, the first one was for hydrogen, this one is for hydroxide ions. Water, since was a part of the system, we don't consider it as a new product. Oxygen gas is considered as the product over here. If there are polyatomic anions, let's say the system is composed of nitrate ion, carbonate ion, sulfate ion, this O is capital, he made a mistake while writing it, phosphate ion, and when they are compared with OH negative, polyatomic ions means ions that are made up of many atoms. As you can see, NO3 is made up of 4 atoms, CO3 is made up of 4 atoms, SO4 is made up of 5 atoms, PO4 is made up of 5 atoms. So in case of polyatomic ions, OH negative is also always the least reactive. So it always goes to the anode and forms oxygen gas. This is not the formula. The formula is O2. O is the subscript. So the same equation which is written over here is also written over here. What does that mean? Only in the case of halide salts, and if they're concentrated, we'll have some other equation, otherwise this equation. Okay, so that's the tip for anions. Now going through these tips may make it a little bit difficult. So I am going to convert aqueous solutions into an easier set of tips. For cations, this is the equation every single time, except copper or silver or gold or platinum is present as a part of cations. In case of anions, for concentrated, okay, for concentrated chloride or bromide or iodide ions, these form. Otherwise, for all other cases, this equation will be used. 4OH negative gives us 2 water molecules. It gives us 1 molecule of oxygen. It gives away 4 electrons. That's it. So you're supposed to memorize this equation as well as this equation. It's aqueous, it's gaseous, it's aqueous, water is a liquid, and oxygen formed is a gas. There you go. If you remember these 2 tips, you're not going to get your answers incorrect. I hope this should make pure sense, good sense, since these 2 tips can get you through electrolysis of aqueous solutions every time perfectly with the correct answer. Do let me know if you don't understand any part of it. Are we clear?
Yes, sir.
Good. So I'll be honest, ये एक बहुत आसान सा रटे वाली तरतीब है. There are 4 metals for which we don't have this equation. Rest for all the metals, you always have this equation. There are 3 negative ions which are present in concentrated form for which we don't have this equation. For rest, every single case we have this equation. So these 2 equations are the most common equations in electrolysis of aqueous solution. Let's move further. Let's take a couple of examples to make it more easier for you. So for you, since theory is a little bit difficult, as soon as we start moving on to the examples, it actually makes the whole thing easy. Okay, let's start with the first example. First example is concentrated sodium chloride NaCl aqueous solution. Now, the student hasn't done it correctly, and I ask my students to do it a little bit differently every time. This is NaCl aqueous. Instead of starting off writing off the answers to the questions, the first thing you should do is to make 4 ions out of the system. The aqueous is always going to form H positive and OH negative ion. Whatever ions the salt forms, write those ions over here. Now, since there are only 3 more columns to the table, the product at cathode or negative electrode, which usually forms after reduction, the product at anode or the positive electrode, which usually forms our oxidation, and the change to electrolyte. This time, the change to electrolyte is not going to be simple. This is going to be a little bit difficult this time. So let's start with writing our answers. Now, before you go with looking up the answers over here, or since you might have already looked up the answers since I was discussing from this very point, why do you think the answer at cathode tells you about hydrogen? Why is the answer hydrogen at cathode? Since the answer is already mentioned over here. All right, reasons, anyone?
Because the sodium is more reactive, so it will stay in the solution, and hydrogen is less reactive, so it will appear up.
Good. Okay, and what did the tip say?
That the less reactive one will appear at the cathode.
No, the tip, not the concept. This is the part of the concept. You're really good with concept. I'm not saying you're answering anything incorrectly. All your answers are correct. But as per the tip, which other metals can really become a part of cathode apart from hydrogen?
It was copper,
Right.
silver, gold, and one more. I forgot that.
Platinum. Very good. Since
Yes.
this formula does not contain copper, silver, gold, or platinum, we'll have hydrogen formed over here. That's what the tip was. And it's really easy. As soon as you look at the formula or the name, think about it. The formula should contain copper, silver, gold, platinum, but this is sodium chloride. It does not have any four of those elements. Let's form hydrogen over here. Simple and easy. The tip works great every time. Even if you don't know or remember the tip, you can always take help from the reactivity series, which you are going to in this chapter or in chapter number 8. You have to remember it by heart. That's actually a prerequisite in O level. Moving on. Next question, same like the previous one. Why do you think the product at anode is chlorine gas?
Um,
What was the tip? The tip said if the solution is concentrated and if the salt consists of either Cl or Br or I, which means chlorine, bromine, or iodine, the respective element is going to form at anode. And it's exactly according to the tip. Since the salt is a concentrated solution, this thing is mentioned, and this is mentioned, we're going to have to form chlorine over here. Hence the equation of chlorine, which is 2Cl negative, that gives us Cl2, the gas, plus it gives away 2 electrons. Now comes the part where I'm going to kick about the importance of writing 4 ions over here. Now I'm going to use a different color. Take a look. Hydrogen ions went to form hydrogen gas at cathode. Chloride ions went to form chlorine at anode. What are we left with? We're left with sodium ions and hydroxide ions. And these are the ones that are going to go to change in electrolyte. What actually happens is that we are only left with two kinds of ions, hydrogen ions and hydroxyl ions, hydroxide ions. They actually literally react with one another as a change to electrolyte and form the compound sodium hydroxide. So we are not just getting products at cathode and anode like we used to do in the previous electrolysis of modern systems. We're actually getting a new product as a change in electrolyte. That's why we had this column in the previous table as well. But since that column was pretty useless in the previous table, it is going to be pretty useful over here since you're forming something new over here. Make sense?
yes, sir.
All three of these, I mean the product get cathode and the product at anode and change to electrolyte. Do all three of these make sense to you?
Yes, sir.
And what about you? Let me know if this makes a little bit of sense to you, if not completely, at least some sense, at least. Right, Wes?
Sir, yeah, to some extent, it's still kind of confusing, but inshallah, I will get the grasp, inshallah.
Good, good. I was hoping the same from you. All right, that's great. So I'm going to erase a couple of parts of it, okay? And let's move on by changing this example. What if I don't take a concentrated solution of sodium chloride. Instead, I take a dilute solution of sodium chloride. Now, the word dilute literally means that I added a very small portion of salt, but I took a huge portion of water. That's what dilute means. The solute is present in very less amount, and there is mostly solvent in the system. So there is mostly water in the system. Sodium chloride is present in very little amount. Again, this is going to form Na positive ions, Cl negative ions, H positive ions, and OH negative ions. So what's different? All four ions is the same. The difference is about this concentration detail. So is it going to bring a difference at the product at cathode or anode or change to electrolyte? Will that be bringing some difference to it? Let's start with product at cathode. What do you think the product at cathode would be?
Hydrogen.
And why do you think that is? First of all, let me tell you that's correct. Secondly, why do you think that is correct?
Because it's less reactive than
Right,
sodium.
great. In case of cations, concentration does not matter. Changing the detail of concentration from concentrated to dilute or from dilute to concentrated does not matter to cation. They only work on the basis of reactivity, hence the reactivity series was so important. And since the formula is same, it does not consist of copper, silver, gold, or platinum, hydrogen is going to form at cathode every single time. So most of the time, you'll wind up writing the same equation for hydrogen every single time if the salt does not contain, of course, the four ions. Okay, what would be the product at anode this time?
And this time it would be hydroxide because it's a dilute solution.
Yeah, the hydroxide ions will go to the anode. What would be the product they are going to form? If we remember the reaction of hydroxide, 4OH negative, they go to the anode, they form two molecules of water, they form one molecule of oxygen, and they give away four electrons. So the product over here is going to be oxygen, since water was already part of the system, right? So yeah, these ions go to the anode, but they form oxygen over there. All right. Okay, I'm gonna again change the colors. So this time, H positive ions went to cathode, OH negative ions went to anode. What are we left with? We are left with these two ions, which are going to form change to electrolyte. But hey, look, Na positive and Cl negative, when they react with one another, they start forming NaCl, which is the salt itself. So basically, in this kind of electrolysis, dilute system, the salt remains the same electrolyte from start till end, and we actually break down water into hydrogen gas and oxygen gas, respectively, at cathode and anode. So that's the
Yes,
case
sir.
where we can break water down into its constituent elements. You know, water is made up of hydrogen and oxygen. So we were capable of breaking down water back into hydrogen and oxygen gases by doing what? By doing by taking a very dilute solution of sodium chloride salt. Make sense?
Yes, sir.
Good, great. If that makes sense, I think we can move down in the table and start on doing some other examples. Okay. Now the student has made mistakes and this is not correct. Okay. All right. If we talk about concentrated potassium iodide aqueous, let's discuss why we get the product that we are getting at cathode, anode, or as a change to electrolyte. Let's start with cathode first. The product written at cathode is hydrogen. Why do we get hydrogen at cathode?
Because potassium is more reactive and it is above the hydrogen in the reactivity series. That's why.
Great. Why do you think we're getting iodine as a product on anode?
Because it's a concentrated solution and we have
Because it's concentrated
halide.
solution. Perfect answer. It's a concentrated halide solution. So that's why iodine is forming at the anode. Now, let me clarify. Ki aqueous, it's going to form K positive ions, it's going to form I negative ions, it's going to form H positive ions, it's going to form lastly OH negative ions. Now iodide ions are forming iodine over here. H positive ions are forming hydrogen over here. What are we left with? We are left with these two ions. What's going to happen to them as a change to electrolyte?
It will become potassium hydroxide.
Your voice is breaking off. I cannot hear you. It will become what?
Potassium hydroxide.
Perfect. That's going to form potassium hydroxide. And the reaction is pretty simple. This K positive reacts with OH negative. It forms KOH, and the name of KOH is potassium hydroxide. So yeah, the student wrote the answer wrong because potassium oxide is not the correct answer. The correct answer is potassium hydroxide. Let's move on to another example. This one's easy. Easy. Let's try this one. Okay. Silver nitrate, AgNO3. This is the first time we have a silver salt. And this is the first time we're dealing with nitrate polyatomic ions. Now the products are already written in front of you. My question is, why are we getting the products that are written over here? Let's start with cathode first. Why are we getting silver at cathode and not hydrogen?
Because there were four specific elements that would come, and silver is one of them, so that's why.
Great, silver is less reactive than hydrogen, and the tip said that if silver is a part of the salt, it's definitely going to form some silver at the cathode. So silver is deposited
Yeah.
at cathode. What about anode?
Um, it is oxygen because the polyatomic ion always stays in the solution, so oxygen would appear.
Good, well done. And lastly, there is a new name, nitric acid written over there. Why do you think we're getting nitric acid from? How do you think we're getting the nitric acid from?
Um,
See, to answer this question, we need to write all the ions, and then you will consider which ions are going to cathode, which ions are going to anode, and there must be two leftover ions. If you combine those ions, you're going to get the formula for nitric acid. So which two ions do you need to combine in order to get nitric acid as an answer written over here? Come on, that should be easy. Okay, let's bifurcate the compound into ions. Afterwards, I believe the answer would be easier to you. So it is silver nitrate, and this is aqueous solution. It's going to give us four ions, silver ions, and then nitrate ions. And the aqueous system is going to give you H positive ions as well as OH negative ions. Now you've already consumed OH negative ions in forming oxygen over here. You've already consumed silver ions in forming silver over here. So nitric acid is formed from which two ions?
nitrate and hydrogen.
Right. So H positive, when reacts with NO3 negative, it forms an acid which is nitric acid, the formula for which is HNO3. That's how you get the nitric acid. I hope now it makes sense, right?
Yes, sir.
If it does, Let's continue with another example. Most of the time, you'll notice that the example for gold and platinum is not a part of the past papers. That is correct. So usually the examples in which something other than hydrogen forms, take a look at this whole column. Hydrogen, 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 hydrogen. No matter I take potassium or I take silver, no matter if I take potassium or calcium or sodium, they are all always going to end up with hydrogen, apart from just one example of silver. So I'm going to use another example after that one. I hope I find that example. Okay, this one's good. Copper sulfate aqueous. The tricky part is there is no dilute or concentrated written next to it. Yet you're supposed to solve it. Go ahead, tell me the reason why you're going to get copper at cathode.
Because it was an exception and it is less reactive than hydrogen.
Great, it is less reactive than hydrogen. So yeah, it would try to get to the electrode cathode. Great. How about oxygen? How do we get oxygen from anode?
It is because SO4 is a polyatomic ion, and so it will be leftovers of that oxygen.
Great. And again, something new. Sulfuric acid. Sulfuric acid is forming as a change to electrolyte. Why do you think that is correct?
Because it will react with hydrogen to form sulfuric acid.
Good. Let's try to do it properly. Copper sulfate is going to form 4 ions, copper 2 plus ions, since sulfate has a charge of negative 2 ions, and this is something that you memorized back in chapter number 3. Water is going to give us, the aqueous solution is going to give us H positive ions as well as OH negative ions. Now, in case of OH negative ions, these go to the anode and form oxygen. As far as copper ions are concerned, they go to cathode and form copper. What are we left with? We're left with H positive ions and SO4 negative 2 ions. So H positive ions tend to react with SO4 negative 2 ions, and they form the acid H2SO4, sulfuric acid. But since there are 2 hydrogen atoms over here, we need to place this specific 2 before the equation in order to balance the number of atoms. There you go. You have the sulfuric acid. H2SO4 is sulfuric acid. Make sense?
Yes, sir.
So copper compounds and sulfur compounds, apart from other compounds, have been used as examples in electrolysis of solutions. Okay, so let's clear it up, move on. Oh, that's actually the bottom of the document. We are done, and there are many examples in here, but sometimes the student has made some writing mistakes. So make sure if you get confused with anything or if you find any mistakes in there, you can correct them.